In an earlier video, we found the degree n Taylor polynomial for sine x at x equals 0. So the degree 5 Taylor polynomial for sine x at x equals 0 is this: x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So that means that if I plug in 1 here, so if I plug in 1 into this Taylor polynomial, let's see, I get 1 minus 1 over 3 factorial plus 1 over 5 factorial. If you do the calculations, this is the decimal approximation 0.8416 and so on. This should be close to the value of sine of 1. So if I plug in 1 to my approximation, it should be close to the value of the function at 1. This approximates the value of f of 1. F of 1 is sine of 1 radian, and that is 0.8414. So you could see, indeed, in this case, plugging in 1 to the Taylor polynomial gives me a value that's pretty darn close to the actual value of plugging in 1 to the function. In fact, these two numbers agree up until the third decimal place, and then they start to be different. So if you take this number and subtract this number, you'll find the error. The error in using this approximation is less than 0.0002. Very small error. This shows that in this case, your Taylor polynomial is a good approximation, even though I plugged in 1. And the Taylor polynomial was designed to behave just like your function f of x at 0. I plugged in a number pretty close to 0, 1, and I still got a good approximation. But here's the main question. Here's the question that I'd like to answer in this video. Let's suppose y of x is the degree n Taylor polynomial for your function f of x at x equals a. The question: how close are the values of y of c and f of c? So in this last example, I took c to be 1. How close is the actual value of what I want to approximate with my approximation? So the answer is given by something known as Taylor's inequality. It says the error, the difference between the actual value and the thing that you're using to approximate the actual value, the error has to be less than or equal to m over n plus 1 factorial times the absolute value of c minus a to the n plus 1 power. And what is this m thing? Where m is any number that satisfies some strange condition. If I take n plus 1 derivatives of my function, m has always got to be bigger than that in absolute value. And this has to be true for values of x that satisfy the distance away from A is less than or equal to c minus A. I know this statement might be a little confusing, but I'm going to do a bunch of examples, and by then I think it'll be made clear. So let's see what Taylor's inequality says in the example of sine x and the degree 5 Taylor polynomial. So in this video, I want to help you understand this, and in the next video, I'll also do some examples of Taylor's inequality to get a good handle on what the statement is actually saying. So, example. In the above case, we took f of x to be sine x. Our a value, that's where we centered the Taylor polynomial. A was 0. The degree n that I took was 5. This is the degree 5 Taylor polynomial because I go up to x to the 5th power. So n is 5. And the value c that is in this theorem was 1 because c was the value I was plugging in. So this says the error in my approximation is less than m. We'll talk about what that is in a minute. Divided by n plus 1 factorial, so 6 factorial, times the absolute value of c, which is 1, minus a, which is 0, to the 6th power, where m is less than or equal to the 6th derivative of sine x. So the 6th derivative of sine x is what I put here. So let's do 6 derivatives. So the derivative of the first derivative is cosine, second derivative, negative sine, third derivative, negative cosine, sine, cosine, negative sine. So the 6th derivative turns out to be negative sine x. That has to be less than m. For values of x, so I'm going to do x minus 0, less than or equal to c, which is 1 minus 0. So what this condition says is that the value of m has to be less than or equal to the absolute value of the graph of sine x on this interval. So this interval, if you just rewrite it, says x has to be less than or equal to 1. So let me draw the graph. Let me draw the graph of negative sine x on the interval from negative 1 to 1. So here's negative 1. Here's 1. And the graph of negative sine x might look something like that. So there's the graph of negative sine x in between negative 1 and 1. These are the x values that satisfy this inequality. So all I have to do is pick a value of m that's always bigger than everything in my picture. So I'm going to take m to equal 1 in this case, because my whole picture, the graph of negative sine x, lands in between the values of 1 and negative 1. So I could take m to be 1. M is always higher than my picture. So over here, I'm going to put in m equals 1. So I get 1 over 6 factorial. Now, 1 over 6 factorial happens to be approximately equal to 0.0013, and so on. So what does Taylor's inequality tell me? It says my error, when I plug in 1 to the degree 5 Taylor polynomial for sine x centered at x equals a is less than this number, 0.0013. We actually already found the error. The actual error is less than 0.0002. So the theorem is true. We did find that the error, the actual error of 0.002 is less than 0.0013. This number gives us an estimate of how bad our approximation could be in the worst possible case. But usually the error will actually be smaller than what we find here. So I'd like to do some more examples. See me in the next video for those.